In last section, we discussed that aromatic compounds, especially we talked about benzene ring, doesn't undergo addition reaction that easily. Rather, it usually undergoes electrophilic substitution reaction. So let me explain to you what is substitution reaction before I go over specific examples. So this is the benzene ring, double bond, single bond, double bond, single bond, double bond. So that's the benzene ring. Don't forget that each corner has a carbon and it's attached to one hydrogen. That's how carbon would have 4 bonds. So that's C6H6. Now, in substitution reaction, what happens is a group comes in. It could be halogen, it could be NO2, it could be SO3H. It comes in and gets bonded here, and hydrogen gets out. So that's how you get substitution reaction. We'll also discuss the mechanism, that means how it actually happens. Again, we'd be going back to resonance when we discuss the mechanism of this reaction. Now, why do they call it electrophilic substitution? Electrophilic means something that loves electron. This double bonds, you can see here, these have loosely bonded electrons. So it's rich in electron. So anything positive, let's assume that is Y plus. Y could be anything. It could be NO2 plus, Cl plus, Br plus. So I can write down some of these species. Cl plus, Br plus, NO2 plus. Any of these would be attracted towards the benzene ring because benzene ring is rich in electrons. The positive charge is always attracted towards electron. And that's the beginning of substitution reaction. Here I'm discussing more specific reactions. Br2, it needs a catalyst. In last slide we discussed that in order to have a substitution reaction, you must have a positively charged species. So in this case, Br2 in presence of FeBr3 forms Br+. So if you look at this reaction at the bottom, Br2, FeBr3 is a catalyst. Now, I just want to mention to you that catalyst is a substance that helps in a reaction, but it doesn't get consumed in a reaction. So in other words, even though temporarily it would give you FeBr4 minus, but FeBr3 releases that Br minus and finally goes back to FeBr3. So keep this in mind. In order to generate positively charged Br plus or Cl plus, you must add a catalyst. In case of bromine, you add FeBr3. So once you get Br plus, here you see the mechanism at the very bottom. Remember, I said that since Br plus is positive, it would show attraction for electrons that benzene ring has. So by drawing this arrow, the black arrow, you are showing that attraction. That means you have electron pair with this double bond, and that gets attracted to the Br, and always you'd see this arrowhead that originates from pair of electrons towards the positive charge, and that's what we're showing you here. So this pi bond donates its electron pair to Br plus, and as a result of that, you'd see what's going to happen. Now here you see that as a result of the addition of Br plus, you get positively charged carbocation like this. Now let me rewrite the last step so that we all understand. And at the beginning, I think it'd be helpful if you write down hydrogens. Each corner has a carbon, and I'm writing down hydrogen so that it'd be CHH6, that the benzene formula. Now when Br plus comes in, which was on the right, on the last slide, this electron pair, let me use a different pen, electron pair from the pi electron of the one of the double bonds, it doesn't matter which one, it donates to Br plus, and Br plus happily accepts electron pair because it does need electron pair, and that leads to a bond formation. It doesn't matter which one gets bonded, so either of these two carbon can be bonded to Br. So let's assume that the first one on the right gets bonded. If that's the case, this is what you're going to get. Actually, I can draw this arrow. That's what you're going to get when Br gets bonded to this carbon. Now don't forget that hydrogens are not gone. Hydrogens are there. It's just for clarity we left out hydrogen. Let's write down this hydrogen so that you know why there is a positive charge at this center. Charges are always conserved. Br came in with positive charge, so it has to be somewhere. And we can find out that this, the carbon, let me draw an asterisk, red asterisk, and that's the carbon which would have positive. Can we calculate that? Yes, you can readily do that by calculating formal charge. So in this particular structure, let's focus around this carbon. There are three bonds. One bond with the hydrogen, with this hydrogen. The other two bonds are with carbon within the ring structure. So it gets the share of 3 electrons. So let's write down here, gets the share of 3 electrons because of the 3 bonds. Now what's the valence electrons, number of valence electrons for carbon? Look at periodic table. Now this is carbon. Now you count from the left to the right along the same line until you get to carbon. So it'd be, you're starting with here on line 2. 1, 2, 3, 4. So it basically is 2s2, 2p2. These are the outermost electrons. So that means there are 4 valence electrons. In other words, carbon is supposed to have 4, and because of the sharing it has 3 outermost electrons. That means it's lost share of 1 electron, and that's why this carbon has a positive charge. Now, next question is resonance possible? Yes, resonance is possible here because there are different locations. These electrons can move, and whenever there is a way that electron can move without moving any atom, it is going to move. So in this case, this double bond where you're showing the arrow can move to this new location, and when it does happen, keep in mind that there is also hydrogen to this so that we don't forget how the positive charges are developed and moves from one center to another center. Okay, now you have a double bond in new location. This is the new location of the double bond. I'm showing you with the red arrow. And that results in a positive charge at this center. Because for the same reason, it lost its double bond or second bond, and if you count, this would have share of 3 electrons when it is supposed to have 4 electrons because that's the carbon. So in other words, now I can see that positive charge has moved from one carbon to another carbon. Now, is there any other resonance structure possible? Yes. Adjacent to this bond that holds that positively charged carbon, there is a double bond. So move that double bond in between this carbon, one of which has the positive charge. So when you do that, this is the new location of that double bond. Again, I'm showing that in red arrow. And now the new position of the positive charge is here. Again, there is a hydrogen at that end. So as you get experience, I don't have to write down all these hydrogens. So how do I know what the positive charge is? There are 2 ways to do that. Either you calculate formal charge, and of course when you calculate formal charge, don't forget in attaching right number of hydrogen atom to that carbon. The other way of looking at it would be look for the carbon that lost its double bond. Obviously, that would be the one that would have positive charge. So these are three carbocations or intermediates before final product is formed. What is the net effect of these three structures? We draw a line like this. This tells us that positive charge is not localized to one carbon center, rather it moves around from one carbon to another carbon, and that gives the stability of this intermediate. Nature always likes something stable, and in other words, is going to form naturally before it gives the final product. Now, final product is this. Let me show you how that happens. Now, you have two choices here. Either hydrogen would leave or Br would leave. If Br leaves, you get back to the original substance. That means it's like going backward in a reaction. And that also happens. But condition should be such that that would favor the reaction, forward reaction to its desired product. So in other words, in this case, hydrogen, when hydrogen leaves at H+, then you end up with bromobenzene. So bromobenzene would look like this. So that's the final product. Now, in the old edition, I'm talking about 2 editions ago, they used to write down this benzene structure with circle in the middle. So I didn't change that. In case you read another book, you'd see that commonly. This is nothing but combination of all possible resonance structures for benzene. So it's called resonance hybrid. But anyway, in your edition of this book has written down one of the resonance structures, and that's why you have bonds like this: double bond, single bond, double bond, and this is bromobenzene as final product. Now I'm showing you the addition of substitution reaction involving Cl2. Again, you need a catalyst so that it generates Cl+. Now here we're not showing that explicitly. This reaction is very similar to Br2 in presence of FeBr3. So first you get Cl+, and then Cl+ gets attracted to the benzene ring. So if you write down with double bond and single bond this benzene ring, it would look like this. Double bond, single bond, double bond. Okay. And then this double bond would be attracted to that ring. And then it finally gets bonded there, and you have intermediate carbocation, which finally loses H+, and you end up with chlorobenzene at the end. Similar would be the case with nitration, NO2 addition reaction. It's called nitration. Nitric acid and sulfuric acid you need to add, and that is going to form NO2+. Again, NO2+ would be attracted to the benzene ring because this is electrophile. NO2+ is electrophile. Having the positive charge, it's electron lover. So that's why it's called electrophile. So that's why double bond would be donating its electron pair to NO2, and eventually mechanism is the same. Eventually hydrogen would leave and you get nitrobenzene. So these mechanisms are all very similar. You need a catalyst that would create a positively charged species, and then that positively charged species will be attracted to the benzene ring. Initially it's going to form a bond with one of those carbon atoms, and finally hydrogen would leave and you end up with a substituted benzene ring. Sulfonation, SO3 in presence of sulfuric acid give you SO3H+. Again, the same story. You have a positively charged species, and that's SO3H+, and that gets bonded to benzene ring, and you finally end up with this benzene sulfonic acid. This is next type of reaction, which would be called Friedel-Crafts alkylation or acylation. method. Now, in this case, aluminum chloride is added so that it removes Cl from alkyl halide. Now, as it removes Cl as Cl minus, you end up with, here the mechanism is not shown, but at some point it's probably shown. Without the hydrogen, I'm showing you this. Now, positive charge is on this carbon, which lost Cl, because Cl goes with AlCl3, and that makes AlCl4 minus. So obviously, plus would be on carbon, and that carbon would get attracted to the benzene ring, just like before. I think it'd be easier to see the mechanism when you write down, rather than a resonance hybrid if you write down like this, the way it's shown in your book. So this would be attracted, and eventually hydrogen, this particular hydrogen would be gone, and you end up with this product. This is isopropyl group. You have a branching next to the last, and that's the branching, and that's why it's isopropyl with 3 carbon. Isopropyl benzene is also called cumene. That's the common name. This is next reaction is called acylation. So this is, in this case, again, just like before, Cl minus would be taken up by AlCl3, and then you'd have CH3CO plus. If we know these mechanisms, it'd be a lot easier for you to predict a reaction. So you don't need to really memorize each and every reaction. So basically, this is going to look like this. CH3, then C double bond O, and then this is plus. And that plus would be attracted to the benzene ring. And rest of the mechanism is the same. Eventually hydrogen would leave, and you end up with this group attached to the benzene ring, and it's called acetophenone.